Hello everyone, in this video we're going to talk about compounds, specifically what types of compounds there are and the types of bonds that go with those different types of compounds. If I take a look back, right, we went over sort of this different types of matter. We talked about how there's mixtures versus pure substances, how there's compounds versus elements, but now we want to dig a little bit deeper and talk about the different types of compounds that there are. So for us, we're going to discuss ionic compounds in this video. We will discuss the nonpolar covalent compounds in a second video, polar covalent compounds in a third video, and then I'll do a fourth video kind of comparing and contrasting all three of these and figuring out, based on a formula, which type of compound are we working with. So the first example I want to do here is just with sodium fluoride, and you may recognize sodium fluoride from, your toothpaste. Sodium fluoride and stannous fluoride are kind of the two big fluoride sources that people put in toothpastes. And what I want to do, if I want to ask myself what type of bond am I forming or what type of compound, I'm just going to start with writing these atoms. So before they bond, just looking at the atoms themselves, right? So I'm going to draw first my sodium atom. So just Na. Sodium has one valence electron, right? And fluorine is just a capital F. Fluorine has its 1, 2, 3, 4, 5, 6, 7 valence electrons. And if I ever want to ask myself what type of bond I'm going to form between two atoms, what I really am asking myself is what's going on with their electronegativities. What are the electronegativities of those two atoms? Is there basically a small difference in electronegativity? Is there no difference at all in their electronegativity? Or is there like a really large difference in electronegativity? So I have a periodic table up here on the right-hand side. If you look, I've got fluorine all the way up here in the upper right spot. Now that makes fluorine very electronegative, right? If you remember your electronegativity trend, as you move up and to the right on the periodic table, you get more electronegative. So more electronegative. As you move down and to the left, you get less electronegative. And we don't count the noble gases, right? So ignore the noble gases. So fluorine is very electronegative. Whereas if we take a look back at sodium, right, sodium is way over here on the left. It's an alkali metal. Sodium's over here on the periodic table. It's not very electronegative at all. So if I look at these two on the periodic table, I can see, without getting specific numbers, that they're really different in terms of electronegativity. They're nowhere near each other on the periodic table, which implies that there's a large difference between the two. Now, there are periodic tables out there. You can go look at the Pauling scales, and there are values of like fluorine's 4 point something, and carbon's 2.1, and iodine's this. And you can look up actual values to compare those. That totally works. Absolutely, you're welcome to do that. For me, in my classes, I just want you guys to have a sense of, are they a small difference, a large difference, or not much of a difference. So if I look at these two, I see that there's a pretty large difference, right? Because if I look at fluorine, I'm just going to write these notes down. Right, fluorine we're going to say is very, very electronegative, which again, right, if you remember electronegativity means that it really wants electrons, right? It pulls hard on electrons. So it pulls hard on electrons. And if anything, if it's going to form an ion, it's going to want to be negative. It's going to want to be negative. And you can imagine that since sodium is not very electronegative, it's way over here, it's basically the opposite for sodium, right? It's not very electronegative. It doesn't want electrons. It doesn't want electrons, right? It's not going to pull on electrons. So not going to pull on electrons. And if anything, instead of wanting to be negative, it's going to want to be positive. Want to be positive, like most all of the metals, right? All the metals are going to form cations if they're in an ionic compound. But the big thing here, like I said before, is that because there's such a very large difference in electronegativity, we're going to see a certain type of bond. So I'm just going to put an extra note here, right, that this is a large difference, so I'm using the capital delta there for difference, a large difference in electronegativity. Oops. Let me write that a different way. So I'll write out the words large difference in electronegativity. Now that's going to inform what happens if you have these two pure elements meet, right? So if you were to have these two pure elements meet, you have a hunk of sodium, you have a fluorine gas. Fluorine really strongly wants electrons. It's the most electronegative element, which means it's going to take electrons from pretty much everything, which is why fluorine gas is so reactive and so toxic. Versus sodium doesn't care about its electron at all. It willingly gives it up. It's going to have a noble gas configuration afterwards, etc. So sodium really doesn't care about that one electron. Fluorine really wants that electron. So what we end up seeing if these two elements meet is that sodium's just going to transfer its electron to fluorine. Fluorine is going to rip that electron away from sodium. So we see a transfer of electrons in this case. And so what we're going to get after this is we no longer have quite the same species, right? So we still have a sodium particle, only now it doesn't have that electron anymore. And we still have a fluorine particle, only now, in addition to its 1, 2, 3, 4, 5, 6, 7 electrons, it just gained sodium's electrons, so now it has 8. So now it has 8 electrons. Now what happens, right, I'm not quite done with drawing these two new particles. What happens here is that sodium, if it loses an electron, I can't say that it's neutral anymore, right? Remember that atoms by themselves, those are neutral. They have the same number of protons and electrons. But now sodium gave up an electron. And if it gives up an electron, and electrons are negative, that means that this sodium should have a positive charge now, right? So sodium has 11 protons, and now it only has 10 electrons though. So I have 10 negative things and 11 positive things, so that's a +1 charge. And we write that +1 as a superscript to the right. So I've got a sodium plus. And fluorine gained that 1 electron, right? So it no longer has the same number of protons as electrons anymore either. Fluorine has 9 protons, and now it has 10 electrons. So now it has one more negative thing than it does positive things, which means it now has a net of -1 charge. So we put a negative for the fluorine. So now these are no longer atoms that are just neutral particles. Now these have charges. And so we call charged particles ions. So now these two friends are ions. And the definition of an ion is just any charged particle. So I'll put ions are charged particles. Charged particles. Or in other words, the number of protons does not equal the number of electrons. You have some dissimilar number like we do in our two cases. Now, why does this happen aside from the fact that fluorine's very electronegative and sodium's not very electronegative? The idea is that in this case, these two ions are much more stable and much happier because of the number of electrons that they have. Right? There is something that was called the noble gas rule or the octet rule. So the noble gas rule, all right, down here, so noble gas rule, also known as the octet rule. I like noble gas rule a little bit better only because not everything has octets, which implies 8. A lot of things have 8, but some things have 2, some have 18. The idea with the noble gas rule, though, is that everything wants to have the same number of electrons as the nearest noble gas. All right, so all atoms want to have the same number of electrons as the nearest noble gas. And so what does that mean, right? So if I take a look at the periodic table, for fluorine, the nearest noble gas here is neon. I'll squiggle that in purple up here on my little periodic table. The nearest noble gas for fluorine is neon. Neon is number 10. Neon has 10 electrons. If you look down here, fluorine has 10 electrons, just like its nearest noble gas. So it's fulfilled the octet rule, fulfilled the noble gas rule. It's more stable now, is the idea. If I take a look at sodium, sodium, its nearest noble gas also is neon, right? So sorry, I got super distracted there. It's nearest noble gas is also neon, right? So if you look forward for sodium, you click forward, and that would be all the way over to argon. You'd have to go forward 7 spots. But if you click backwards 1 spot, that's neon, right? So sodium's element 11. If you move forward 7, you get up to 18, which is argon. Again, sodium's 11, but if you go back 1 to 10, that's neon, and that's also 10 electrons, which sodium also has 10 electrons in this case. So both of these atoms are able to achieve meet the noble gas rule, or achieve full shells is the idea, full electron shells. So they're much more stable. So I'll just put they become more stable, and that's really the driving force behind like why things bond. So I want to talk a little bit more about what these particles look like, right? You start off with a sodium particle and a fluorine particle. You end up with a sodium ion particle and a fluoride ion particle. So we're just saying that sodium fluoride, right, Na and F, if you had these two elements, they would interact to give you Na plus, F minus. And the important thing about the ionic bonds or ionic compounds here is that these are separate particles. These are two ions, right? These are both ions. But the ions come in two flavors, right? We've got cations, which are the positive things, which are always positive, and anions, which are always negative, right? Those are the two types of ions that we have. And when you have these sodium and fluorides, if you take a look at like an actual sodium fluoride crystal, you're going to see that you have a sodium, and then a fluoride, and then a sodium, and then a fluoride. And then this repeats over and over and over again in numbers of particles that we don't really have names for, right? Billions of trillions of quadrillions of Google, etc. It's just so high. And the reason why these are attracted to each other, right, is that you notice that I'm just putting a negative next to a positive, a negative next to a positive, a negative next to a positive. And so these are being attracted to one another by the electromagnetic force. So this is just attracted by the electromagnetic force. The electromagnetic force, right? Because you have a positive thing being attracted to a negative thing. And that's all that's really going on here. And that's what this drawing over here on the right-hand side is trying to show you, right? You got the purple circles and the green circles, and they just alternate in this big 3D lattice. And they're all individual particles, individual spheres. So they're not connected, right? So the idea is that, and we'll talk about this in future videos, but in theory, I could take this purple one and water could solvate that and remove just that purple one. The whole block doesn't have to come. And then water could surround this green one and solvate it, and that could pop off. And again, the whole block doesn't have to come because these are not connected in the ways that like a covalent compound is connected. And we'll talk more about that in a second. But these are all individual particles. They're all separate particles. So you'll either see people draw out individual circles, which I kind of like doing, or sometimes people, to emphasize that they're separate particles, will put those separate particles in square brackets to indicate that those are separate particles. That works too. However you want to show it, as long as they have separate particles, as long as they're separated somehow, then you're going to be set. What we don't want to see is something like NaF, where you have a line between them. That's going to be super misleading. We'll talk more about covalent bonds later, but you don't have a line between the two things. They're not connected in that way. They're just individual magnets, individual particles attracted to one another. Now let's do another example, magnesium chloride here, just one more to emphasize how this works. So again, I will draw atoms. So here are my atoms. I will first draw magnesium. So we have Mg. Magnesium apparently has 2 valence electrons because it's in the second group. I'm going to draw 2 chlorine atoms. So I've got a Cl, 1, 2, 3, 4, 5, 6, 7, and another Cl, 1, 2, 3, 4, 5, 6, 7. So I've got my 2 chlorine atoms. I did the 2 because there's a subscript there. And again, if I look at the periodic table, I'm going to see that these are also very far apart. There is also a large difference in electronegativity. I don't have a little drawing on this one, but if I just give you a little periodic table drawing here, right, magnesium is going to be roughly right here. So you have magnesium over here in the alkaline metals, and then chlorine is going to be roughly over here. And so, again, there's going to be a large difference in electronegativity. They're on different sides of the periodic table. They're crossing that big transition metal gap, for example. And so if I'm looking at this, I'm also thinking that this is going to be a very large difference. A large difference in their electronegativities, which is going to be my hint that this should be ionic. It should be an ionic bond, an ionic compound. Because again, right, if I take a look at these different particles, chlorine is very electronegative, right? Really wants electrons, versus magnesium is not very electronegative, doesn't really want electrons as much. So not very electronegative, doesn't want its electrons, right? It's going to give them up fairly easily. And so we see the same thing that we saw in the last example here, right? These particles, if you took elemental magnesium and you took elemental chlorine, they're going to react, and the chlorine is going to take an electron, right? So if I look at this chlorine up here, it's going to take 1 electron so that it can get up to 8 and look like the nearest noble gas, argon. And magnesium is going to give the other one up to the other chlorine, so that other chlorine can also have 8 around it and look like its nearest noble gas, argon. And so if I redraw these here, I've got magnesium. But now magnesium, right, magnesium still has its 12 protons. And it used to have 12 electrons over here, but it just gave them up, so now it has 10 electrons, which leaves us with a +2 charge. Now I've got my chlorine. Apparently I've got 2 chlorines, right? 1, 2, 3, 4, 5, 6, 7 electrons. I've got the other one, 1, 2, 3, 4, 5, 6, 7 electrons. Each of those chlorine atoms picked up 1 electron from the magnesium. So now there's an extra electron here. And these chlorine atoms, right, the number of protons that chlorine has are 17. They each picked up 1 electron to have 18, so they're all at -1 charges right now. -1. So -1, -1. And again, these are separate particles also, right? These are still individual pieces. And so now I have this new compound, magnesium chloride. Again, you'll notice that the number of electrons that magnesium has now is 10, so it has the same number of electrons as neon, its nearest noble gas. And chlorine, each of those chlorine atoms have 18 now, which makes it look like argon, which are its nearest noble gas. Right? Argon is chlorine's nearest noble gas. It just needs to gain 1 electron to look like that. So like argon, like neon. And this would be another example of a ionic compound. Again, these would just be attracted to one another because of the electromagnetic force, because negatives and positives will attract each other. That's the idea. So magnesium chloride would also be an example of an ionic compound because there's a large difference in electronegativity. And that's what you're going to see for all ionic compounds. We tend to classify them as ionic because they have a large difference in electronegativity. So kind of back to this flow chart for the different types of compounds. We're going to fill these in for each one of these that we do. But for ionic, I want to emphasize that for ionic, the idea is that we have a large difference in electronegativity here. So that delta En, there's a big difference between the electronegativities of the 2 atoms in the bond that you're talking about. And because of that, we see that there was at some point in the past a transfer of electrons, that one element stole electrons from another one to create that ion. And since it's ionic, that means that we're dealing with full charges here, since actual full electrons were moved from one element to another. So that means you expect to see a +1 on something or a -1, or a +2 or a -3 or something drawn on an ion. And what we're going to do next is I'm going to talk about nonpolar covalent and then polar covalent ones in future videos. So keep an eye out for part 2, which will be all about nonpolar covalent compounds. Thanks so much.